Welcome to the presentation of the paper Fast Multiview Rendering for Real-Time Applications. My name is Johannes Unterguggenberger from TU Wien. It is pretty obvious that we need to render multiple views for virtual reality applications. We need a separate view for each eye, or maybe even more views depending on the particular VR headset used. But there are also use cases for even more views, like visibility algorithms. Maybe to create a potentially visible set of primitives based on multiple ID buffers, each one of them produced by rendering one view. Another use case can be the creation of multiple shadow maps for different light sources. But how do you program the rendering of multiple views in a real-time application? There are many ways to do it, and different methods have been suggested in previous work, especially for stereo rendering. Yet it is unclear how these different approaches perform for different usage scenarios and if they scale nicely on current GPUs. The most straightforward way to implement it would be to just invoke a given graphics pipeline n times, once per view. We call this approach multipass. To render one view, we just activate the first frame buffer. Set the view matrix for the first view, which will be used in the vertex shader to transform the geometry for view 1, and issue the draw calls. The first view will be rendered. Actually, there can, or in most cases will, be multiple draw calls to render a scene. In all of my following slides, I will not refer to this again, but all the diagrams I am going to show you have this loop going from 1 to D, which shall indicate that multiple draw calls can actually be needed for drawing the result of one view. In an actual application, this would behave about like the following animation illustrates. After rendering of one view has completed, we perform all these steps all over again. Another frame buffer is activated. The next view matrix is set, and the draw calls for view 2 are issued. This is repeated n times until all the views have been rendered. We describe such a pipeline with the pipeline notation that is displayed at the bottom right. The last parameter of the pipeline function refers to the frame buffers. It means that all of them are separate in this case. The arrow, the middle parameter, refers to the way how geometry is processed throughout the pipeline. In this case, geometry is just moving straight through the pipeline, so to say, requiring only vertex and fragment shaders. The first parameter, the n, refers to the number of pipeline invocations with respect to the number of views. In this case, we have to issue all our draw calls n times, once per view. This multipass approach seems like a very naive and brute force approach, but already here we have some possibilities for variations. We can use a single big partitioned frame buffer instead of separate frame buffers. Since we only have one frame buffer, it only has to be activated once. But we must loop n times also for this pipeline variant. Instead of setting a different frame buffer for each view, we are setting a different viewport in the same frame buffer. Issuing the draw calls for the current views renders only into that viewport. The pipeline description function for this variant has the following parts. N as the first parameter, meaning that all draw calls have to be issued n times, once per view again. The way geometry is pathing through the pipeline stays the same. And for the third parameter, we are specifying that the big partitioned frame buffer is going to be used. In addition, we must use clipping to restrict rendering to a certain region of it, indicated by the fourth parameter. Now, does a different frame buffer format already make a difference? Let's compare the frame times of those two approaches by just calculating the relative frame times, subtracting the milliseconds of the approach with the separate frame buffers from the milliseconds of the second approach, the one with the big partitioned frame buffer. This yields the following results. Depending on the graphics card used, one or the other method is slightly faster. Results below the line at 0 milliseconds indicate that the variant with the big partitioned frame buffer has been faster, while results above the line indicate that the variant with separate frame buffers has been faster. The results vary a bit depending on the GPU, but for many of the GPUs, the results lie just within 0.5 milliseconds. Therefore, we cannot really recognize a clear winner in this competition. All the results that I am showing you here on this slide and also in the following slides until we get to the last chapter of this talk are based on measurements of ID buffer generation. Every view that is produced contains just the primitive IDs of rendered triangles. We chose this as the basis for our evaluations because ID buffer generation has little vertex shader and fragment shader load, which enables us to focus on the pure pipeline characteristics. And additionally, the view thruster overlap, so the potential for optimizations of certain pipeline variants is maintained because geometry can be shared across views. Speaking of geometry, that brings me to the second chapter, where we are investigating how geometry is processed by a graphics pipeline. Or in other words, let's take a look at the journey of the triangles through different variants of graphics pipelines. In the case of our multipass pipelines, the journey of the triangles is straightforward, in every loop iteration and for every draw call. Triangles are just moving straight through the pipeline, which only has a vertex and fragment shader. One triangle remains one triangle throughout the pipeline and eventually is being rasterized into the active Framebuffer region if it does not get culled before that. So the point here is that the loop to produce all n views is on the CPU side. Using different pipeline variants, this loop can be transferred into a GPU loop, namely into a geometry shader. All view matrices are loaded into a buffer and can be accessed from the geometry shader. Triangles are only submitted once for all view matrices. And the geometry amplification happens within the geometry shader, and triangles are created from one input triangle, one for each view. Each one of these triangles is transformed individually and rasterized into a different Framebuffer layer. Please note that in the animation only 3 Framebuffer layers are highlighted exemplarily for all n layers. Actually, when rendering n views, all n layers would be rendered into simultaneously, but the animation shows only 3. Let's look at the animation once again for multiple triangles. The pipeline function which we use to describe such a pipeline is the following. Its first parameter is 1, because the draw calls are only issued once for all n views. The second parameter indicates that geometry is amplified using a loop in the geometry shader. And the third parameter refers to the Framebuffer layout, which is a layered Framebuffer in this case with n layers. There is another variant which is geometry shader based and works very similar to this. However, it does not require a loop in the geometry shader, but instead uses a feature called geometry shader instancing. Again, while the previously introduced variant uses a loop in the geometry shader and iterates through all the view matrices using that loop, the geometry shader instancing based method gets its geometry shader invoked n times, each time with a different instance ID, which can be used to get the right view matrix. Do these geometry shader-based variants perform better than the simple multipass approach? Millisecond differences below the 0 milliseconds line indicate that the geometry shader instancing-based pipeline is performing better than multipass. Millisecond differences above the 0 line indicate the opposite. Multipass has been faster than geometry shader instancing. These box plots show the accumulated data from all test cases, which also include tests with different numbers of views. The more views are produced, the slower the geometry shader-based methods get. This is actually not what we expected, is it? Anyways, we clearly need something else. But before we take a look at other options, I would like to shift from comparisons in milliseconds to comparisons in percent. What has changed is the representation. Multipass is used as the baseline, and the performance of the geometry shader instancing-based technique is measured in percent of the baseline. That means in percent of multipass performance. And now, which different configurations have we measured? We have performed complete measurements on 6 different GPUs. We've measured on different generations of NVIDIA GPUs, including Maxwell, Pascal, and Turing microarchitectures. We have performed the measurements in 6 different scenes. We took smaller scenes like the well-known sponsor, and also larger scenes like the Amazon Bistro or the San Miguel scene. The scenes were tested in different geometry representations, which concretely means finer or more coarsely subdivided. We have applied CPU-based view frustum culling in order to create realistic usage circumstances. The degree of scene subdivision leads to varying numbers of draw calls per view position, or per set of view positions, for those pipeline variants that only require all draw calls to be submitted once in order to produce all n views. All tests were performed in 4 different view configurations: stereo rendering, 4 matrices, a 4x4 grid yielding 16 different view positions, and also a 8x4 grid yielding 32 different view positions. Furthermore, all measurements have been performed in different resolutions. We have simulated additional vertex shader load to test what happens if an application requires demanding vertex shaders. To simulate increased fragment shader load, we have performed tests with G-buffer rendering. And finally, we tested the influence of overlap between the view thruster. But before we take a deeper look at the measurements, we still need fast techniques. A few years ago, an extension has been proposed and implemented by many GPU vendors. In the OpenGL world, its name is OVR Multiview, and it offers hardware-accelerated rendering of multiple views. That is, exactly what we are looking for. Let's see how a pipeline diagram of hardware-accelerated multiview would look like, but first, let's remember what geometry shader instancing looked like. The key point here is where the geometry amplification happens, in the geometry shader. Now let's switch to hardware-accelerated multiview. The view matrices need to be consumed in the vertex shader instead of in a geometry shader, and geometry amplification happens somewhere before the vertex shader. This is indicated with the dashed circle containing a question mark. It is a question mark because we do not know exactly how geometry is amplified, since its implementation is vendor specific. We describe hardware-accelerated multiview with the following pipeline function. There is only one invocation of all the draw calls. Geometry amplification happens probably somewhere before the vertex shader. In terms of usage, we definitely get multiple invocations of vertex shaders, each with a different view ID. We use this view ID to transform a vertex with respect to the corresponding view. The Framebuffer layout is one single layered Framebuffer with n layers. Let's watch the journey of the triangles for this case. After geometry has been amplified by the hardware extension, it is rendered into all n views in parallel. Also here I have just animated 3 different target layers, but please imagine that all n layers are rendered into in parallel, one for each of the n views. Let's watch the animation of this hardware-accelerated multiview again. And then let's see if that finally brings some performance improvement over multipass. First of all, we only have NVIDIA GPUs left in the diagram because AMD does not support hardware-accelerated multiview. Secondly, we can finally see some good performance. The median of the 2 high-end Turing GPUs indicates that using the OVR multiview extension takes approximately 25% less time to render a scene compared to multipass. However, on other GPUs the performance numbers are still not better than multipass. Shouldn't that be the fastest possible way? We need to take a closer look on hardware-accelerated multiview rendering. The question is, how many views can actually be fully hardware-accelerated? The Pascal white paper says, with Pascal's SMP engine, which supports 2 separate projection centers, the GPU can render the 2 stereo projections directly in a single rendering pass. And the Turing white paper says, Turing hardware supports up to 4 views per pass and up to 32 views are supported at the API level. So on Pascal 2 views can be rendered with full hardware acceleration, and on Turing 4 views can be rendered with full hardware acceleration. But 32 views are supported on the API level. Shouldn't the API schedule rendering of more than 4 views in the most optimal manner? We have to check. We are testing what happens if we only produce 2 views at a time, but fully hardware accelerated on Pascal. And on Turing, we would always produce 4 views at a time, also fully utilizing hardware acceleration. This has the effect that we increase loop iterations once again to n over 2 on Pascal and to n over 4 on Turing. Let's look at the adapted pipeline diagram. Here we see the return of multiple iterations. n/4 iterations in this example in order to produce n views, each of which is rendered into a frame buffer with 4 layers, one for each hardware accelerated view. Next iteration, next frame buffer. And so many iterations until all n views have been rendered into n/4 frame buffers. In the vertex shader, we just have to make sure to get the right view matrix. But other than that, the rest is just the same as with the other OVR multi-view pipeline variant. The differences are that we have more iterations are rendering fewer views, but all of them fully hardware accelerated. Back to the performance comparisons. This is the same diagram that I've shown before making the adaptations to the OVR multi-view pipelines. Let's now switch to the new, fully hardware accelerated variants with more iterations. Oh, that looks better. Performance is better than multipass in most of the cases on all GPUs. On NVIDIA's high-end Turing GPUs, actually in virtually all cases. I would now like to define those fully hardware accelerated variants as the new baseline for further diagrams. This slide shows different other pipeline variants with the performance compared to fully hardware accelerated multi-view. Let's go through the pipelines one by one. First one is our well-known multipass. In the second column, you can see the second multipass variant, the one which uses a big partitioned frame buffer. In the third column, we have an optimized version of the geometry shader amplification variant. Column 4 shows an optimized version of the geometry shader instancing variant. In column 5, we can see the original version of hardware accelerated multi-view that makes use of the graphics API in order to render up to 32 views with one single pass for all n views. The last two columns show further optimized geometry shader based variants. What kind of optimizations are those? Let's see. To start, let us take another look back at our initial variant of geometry shader instancing. There is only one pass to produce all n views. During our investigations, we were able to find out that also switching these variants to versions that do only produce 4 views in one pass and increasing the number of passes accordingly leads to significant performance increases. This version needs to submit all draw calls n/4 times as often as the version with only one draw call. But this leads to better work distribution on the GPU and finally to a significantly increased performance despite the higher number of draw calls. n/4 iterations are required to produce all n views. Each batch of up to 4 views is rendered in a separate frame buffer. Furthermore, we discovered that adding custom view frustum culling and backface culling to the geometry shader increased performance even more. Culling reduces the amount of work that has to be processed in the geometry shader and in subsequent stages of a graphics pipeline. The two geometry shader based pipeline variants that utilize all of the optimizations presented in the previous slides are those in the two rightmost columns of the diagram. Fully hardware accelerated multi-view seems to be faster in almost all cases, but there is an interesting region that is definitely worth being further investigated. There are some cases where our shiny new optimized pipeline variants are able to outperform hardware accelerated multi-view. Let's finally look at the performance trends that we were able to spot during our evaluation of the results. Which are the cases where the optimized geometry shader variants are faster? Since our focus is on them for now, I'll scale the arrows to the quartiles of the geometry shader instancing variant. Let us investigate how the results change when we only take the test cases into account that produced 16 or 32 views. And additionally, let us restrict the data to the larger test scenes like Bistro and San Miguel. That is good news for our geometry shader variants. They are showing better performance than the fully hardware accelerated pipelines in the majority of test cases. On the contrary, this means that they are probably not doing too well with few views, referring to our test cases with 2 or 4 views. Also, for smaller test scenes the results can look different. What we found out is that for smaller scenes, the pipeline performances move closer together. That actually means the larger scenes are more interesting to analyze because they probably point out performance characteristics better. Remember, however, these diagrams are generated across all NVIDIA GPUs, so there can still be huge differences across the different hardware generations. Let's see what happens on Turing microarchitecture GPUs. Okay, fully hardware-accelerated multi-view rendering is coping particularly well on Turing. All other pipeline variants lose performance compared to it. However, there is still a bright spot with respect to the compared pipelines here. The optimized geometry shader instancing variant has its median value pretty much exactly at the 100% value. Overall, we can say that for producing many views in large scenes, geometry shader instancing is able to show very competitive performance even on the Turing microarchitecture. That is, as pointed out, only on Turing, the performance of optimized geometry shader instancing becomes even better on older microarchitectures of the Maxwell and Pascal generations. Let's see. Now these are some very cool results. Both of our optimized geometry shader variants strictly outperform hardware-accelerated multi-view rendering on older NVIDIA microarchitectures for many views in large scenes, taking only about 70% of the rendering time to produce all the views. Not only on older generations we could observe good performance, but also generally on lower tier NVIDIA GPUs. Let us restrict the results to the two low-tier GPUs that participated in our tests. And also in this case, we can see that the two geometry shader-based variants outperform fully hardware-accelerated multi-view in virtually all test cases with many views in large scenes. Let us investigate some more parameters. What happens if we increase the vertex shader load drastically? We can observe that performance numbers shift a bit in favor of fully hardware-accelerated multi-view, but our geometry shader-based variants are still showing good performance. Interestingly, if you pay attention to columns 3 and 4, the purple and blue one, it is obvious that the geometry shader-based variants, which require only one pass of draw calls to produce all n views, catch up in terms of performance. This is expected, however, because fewer vertex shader invocations happen in these cases. The geometry is multiplied after the vertex shader, in a geometry shader loop or by the means of geometry shader instancing. Let us remove the filter to the low-tier GPUs and take a look at the complete picture across all GPUs once again. The general trend that performance shifts in favor of fully hardware-accelerated multi-view is noticeable, but in these cases, geometry shader-based variants with only one pass of draw calls generally perform better. The message here is that if you know your specific use case, you can make informed decisions about choosing the right pipeline variant. We have looked at increased vertex shader load. Now let's take a look at what happens with increased fragment shader load. The performance numbers here are based on our test cases from gbuffer rendering. Fully hardware-accelerated multi-view is able to gain ground with respect to all other pipeline variants. We attribute this to the shading cache, which is a feature of NVIDIA's hardware extension. Increased fragment shader load does not have such a huge impact on performance when using the hardware extension, while other pipeline variants do not use any cache and suffer the full impact of increased fragment shader load. Before I come to the end of my presentation, let us investigate one more interesting case, the effects of Viewport discrepancy. All test results that we have looked at so far are from test cases depicted on the left-hand side on this slide. All views are close to each other and the overlap of geometry rendered from the different views is generally rather big. Views are only slightly offset from each other and always look in the same direction. There are other use cases where there is only little or maybe no overlap at all. This use case is illustrated on the right-hand side. Imagine, for instance, producing shadow maps for multiple spotlights distributed across a scene. The view thruster of these spotlights might not overlap, or maybe overlap only a little bit. How does such a scenario impact performance of multi-view rendering? Quite severely, as it turns out. While our optimized geometry shader-based variants show similar performance to fully hardware-accelerated multi-view, all of them are quite heavily outperformed by simple multipass, the naive, quote-unquote, techniques from the very beginning of this presentation. They only require 60% of the rendering time of fully hardware-accelerated multi-view, often even less. For incoherent view thruster, the geometry cache of hardware-accelerated multi-view becomes a burden. Also in the case of geometry shader-based techniques, our optimizations that cull geometry are not effective anymore, and the geometry output overhead per input primitive has a negative impact on performance. All in all, we recommend simple multipass for incoherent view thruster based on our empirical data. Let us change the baseline once again to multipass in this case. it can be seen that other pipeline variants take generally 150% of multipass rendering time or much more, which is a very significant difference. And, by the way, this is what performance on our AMD GPUs looked like all along for all of our test cases. Multipass outperforms every other pipeline variant in any test case on AMD. With this, I would like to conclude my talk, where we have investigated different variants of graphics pipelines. We have examined the journey of triangles throughout different pipelines and especially focused on where the geometry is amplified. We have seen hardware support for accelerated multi-view rendering. We saw how geometry shader-based variants can be optimized so that they reach competitive performance compared to hardware-accelerated multi-view in many cases, while still offering full support for custom tessellation and geometry shaders. And we have looked through the performance trends of several selected test cases. I would like to thank you for your attention during the presentation of fast multi-view rendering for real-time applications.